Assalamu alaikum. So today we will be discussing on unit 2 that is your power factor improvement techniques. Okay, improvement techniques. So basically till now you might have heard this term a lot, and your basic aim, or most of you feel like engineering is of improving your power factor. So that is the ultimate. Most of you may feel like that. Okay, so you might have started disliking about your inductor, and you might be feeling good about your capacitor. So till now you might feel that an inductor is a villain of your electrical engineering, and your capacitor may be your hero. So if you are feeling like that, it is not like that. Okay, so most of the load, actually most of the load which you are using in the industry are your induction motors, three-phase induction motors. Okay, so and if you are representing an induction motor, you have to use a resistor, and you have to use your inductor. So this induction motor takes a large amount of power on you can say that generating power. Okay, so and then it gives the production level. It makes your production also. So if you are representing it with R and L, okay, this R and L, so because of this only the power factor lags. Okay, and that makes you there has a lagging power factor, and then you might be feeling like that ki why we are using inductor, we should use capacitors. So it's not like that, because we are using an induction motors. If you are using an AC motors, so or most of the motor except your synchronous motor in your overexcited state, every motors have an inbuilt magnetic field, and so it will be represented in terms of resistance and inductance. Okay, so, for if you are taking something in a mechanical part, if you are taking torque, if you are developing torque, if you are making a speed in the motors, okay, so you have to utilize this magnetic field energy. Okay, and then so ultimate this magnetic field, what it makes, that it causes the distorted shape of your supply, and then it lags your current with the voltage, and then it's decrement your power factors. Okay, so it's like if you want something, you have to pay for something. It's like that. Okay, so first we will be discuss that why we are discussing this topic too much. Okay, why we are discussing this topic too much. Okay, so actually if you see, I am just taking a simple example. I am taking an induction motor with a resistance of 1 ohm, and your inductor has a 10 j ohm, and it is supplied by your single phase supply, that is your 230 volt. Okay, and your 50 hertz. So this is the circuit. So if you calculate this impedance, this is the Z is your 1 plus 10J is your Z. And if you want to calculate your current, so current will be 230, that is your voltage, at an angle 0 degree, divided by 1 plus 10J. Okay, so if you calculate this thing, so you will get approximately 22.89 at an angle minus 84.29 degree. Okay, so better calculate it and then just justify it if I am correct. So this is the current you are getting. Now what happens if I want to calculate the kVA? How much kVA is supplied by the circuit? How much kVA it takes? So here the amount is voltage into current, we can say that. So voltage is 230 volt and your current, the magnitude of the current is 22.89. okay, so this will give you 5264.7 VA. okay, and if I want to convert it into kVA, so it will be 5.264 kVA. Now so this is the whole scenario. Here your induction motor has this this resistance and this your inductance impedance. So you are getting this thing. Now what I do, I put this induction motor and I shunt with a capacitor. This same circuit, I just put a extra capacitor here. Now let's check what happens with our calculation. So the same supply, 230 volt I'm supplying and 50 hertz I'm supplying here, and here now I will calculate our current. okay, now this current so here also 1 ohm and 10 J. Here I'm just putting value of 10 J minus J. okay, actually if you are using 10 plus 10 for your inductance, so you have to use minus 10 for your capacitance. So here this is the whole scenario. Now let's calculate first the Z. So Z seen by your supply. So I'll calculate Z. You can say these two are a parallel circuit. So 1 plus 10J, okay, multiplied by minus 10J, and if you want to divide, so is 1 plus 10J plus or minus 10J. So it's simply R1 into R2 upon R1 plus R2. okay, so what you will get, you'll cancel it out and you will get 100 minus 10J. okay, so this is the impedance you are getting. Now if you want to calculate the current, so 230 at an angle 0 divided by 100 minus 10J, so you will get current somewhere around 2.29 at an angle 5.71. okay, 5.71. and if you want to calculate the kVA, okay, so if you want to calculate the kVA, so I'll just put out 230 into 2.29 and that will be equal to 0.526 kVA. So if you check around what happens here, if you see the calculation, overall calculation, the two calculation, if you check around, what happens here is that this circuit, this circuit which has an induction motor, it takes current approximately 23 ampere. okay, this current is 23 ampere, and this current is having the same induction motor, just we are putting a shunt capacitor. This current, the current level is 2.29. okay, so what happens, the current here, the current is more, here the current is less. okay, next check out the kVA rating. Here the kVA rating is more, here the kVA rating is less. Okay, so sir, we don't understand. Okay, current is good, current is high here, current is less here. So what will be the effect? What will be the effect? So if the current is high, you have to require large cross sectional area of a wire, like you have to require thick wire, thick cross sectional area wire. Okay, so thick cross sectional area wire means you have to invest more on wiring. Okay, so it will be costlier. Here the cross sectional area will be less because the current requirement will be less, so cross sectional area will be decreased. Okay, so this area will be less, so which is more economical. Considering the current, it is more economical. Secondly, here we have directly considered our supply, we have directly considered our load. We haven't considered any middle path resistance. Okay, so if you are considering any middle path resistance, this resistance, that is because of your transmission line resistance, you can say. If you are considering this transmission line resistance, as the current is more here, the drop will be more. Okay, I into R, the drop will be more here, and here as the current is low, the drop will be less here. So what happens to the drop? This will lead to voltage the voltage regulation will be poor voltage regulation. Okay, so here the most of the drop occurs in the transmission. Here as the current is less, the drop will be less, so voltage regulation will be good. Okay, will be good. Next is your losses. So here as the current is more and resistance is there, so that will leads to your more losses, I square R loss, that is your copper loss in your conductor, in your transmission line. This I square R loss or copper loss will be more here. Okay, here the copper loss will be less. So these are the factors that are influenced just by adding a capacitor, so this affects your system. Okay, so here I haven't still not said any word regarding your power factor. I have just shown you the advantage of adding a shunt capacitor. So this shunt capacitor, what it affects, what it does here, on a basic point of view, if you check around, it affects your impedance. So if you are adding a capacitor here, what happens to the impedance? It is 100 minus 10J. Okay, and the impedance was 1 plus 10J here. So look at the real and the imaginary part. Here you have less real part and more imaginary part, but here you have more real part and less imaginary part. So your most of the power is invested, you can say most of the power is invested in real power. Okay, here most of the power is invested in your reactive power. Okay, so that is the major difference on power factor things. I hope you got it clear that by adding a capacitor, simple capacitor, how it can affect your circuit. Okay, so these are the major causes. Like overall view, if you can see here, the current increases means cross sectional area you will require more cross sectional area. So here the kVA rating increases. Okay, without any capacitor, the kVA rating increases. Here if you check it around, the current decreases, cross sectional area decreases, kVA rating decreases. This will lead to your drop in your transmission line. As the current is high, more drop will be there in the transmission line, and that will lead to poor voltage regulation. Here the drop will be less, and that will be lead to very good voltage regulation. Okay, next is your I square R loss. The copper loss will be occurring in your transmission line, will be more here compared to the this part. Okay, so now this is the problem that is occurring because of your adding without not adding a capacitor. Okay, so most of our loads are, as I have already told you, is your induction motor load or inductive loads. Okay, so most of our circuits is based on this. So what are the methods how we can use this? As you have just seen, by just simply adding a capacitor, it can affect largely. So if there are some methods like you're adding a static capacitor. So this static capacitor is simply adding a shunt capacitor. Okay, mostly this shunt capacitor are added to directly to the load. Okay, directly to the load, like across your induction motor, across your motor, that any motor where you want to do this shunt capacitor. But you can add a series capacitor also, but this series capacitor is added in the transmission line power factor improvement, transmission line. Okay, so this transmission line, you generally represent a transmission line with a resistance with an inductor. Okay, so now if you are adding a capacitor here, so this is your JXL and this will be your minus JXC. So overall here the your overall this reactance will decrease. Okay, so overall reactance will decrease. So this also helps in your improvement of your power factor. Okay, so this is what happens with your static capacitor, adding a shunt capacitor directly to the load, across a load, if you are attaching it to the parallelly. Okay, so if you don't want to use parallel capacitors, you just use series capacitor, but the applications are different. Here it will be directly to the load, here it will be directly to the transmission line. Okay, next is your what this has an advantage is that it has a low initial cost. Initial cost is very low. Okay, initial cost is very low, and your maintenance will be less. Maintenance definitely you don't have to do a maintenance purpose. Maintenance will be less. Okay, so this these are generally used in a low cost plant. Okay, low cost plant or low cost transmission line. Next is your next better perspective is the synchronous machine. Generally it is also called as your synchronous motor. Specifically if I say synchronous motor in overexcited state. So this synchronous machine synchronous motor has a field winding. Better read the machine topics and their V inverted V curve, the most important part of electrical engineering. So this is your field excitation. So if you have more field excitation, if you operate synchronous motor at overexcited state, then it acts as a power factor corrector device. Okay, power factor corrector device, or you can also set synchronous phase advancer. Okay, so these are the two important methods, or these are the two important devices that are used for your power factor improvement. Next is your where you will be installing this. What is the place? So if you are considering a transmission line, if you are considering a transmission line, you should install it at a receiving end. Okay, so there are two ends, receiving end and sending end, or if you want to install a power factor corrector device, please install it at the receiving end. This is the generally asked question. So we'll be discussing more numerical on this, and then you will be have a clarity on it. Okay, thank you.